Okay, so I want to follow up on the second video with the rest of the notes here, on the rest of the, what again, considering basic integration techniques. And so we had left off with 4a, and that was a perfect U substitution because we had the 40 minus 8x that was a multiple of our du. Here, we just have 40. And one thing that I know is a good characteristic, I guess, sign or something to look for is that if you're not off by 1 degree, it's not going to be a U substitution, or you're off by 2 degrees. We're quadratic and the denominator, and then it's just a constant. That's 2 degrees. So U substitution definitely does not make sense. But then I'm hoping we realize that this needs to be, an inverse trig function. But it's not quite a squared minus u squared, which is what we would need for inverse sine. So we just need to complete the square. Because if it were, like a squared minus u squared, then so then that's exactly what we would get for inverse sine. So what I'm going to do is, I like to manipulate this. I like my x squared positive, so I'm going to factor out a negative just so I can see this. I don't know, just how my brain works. So x squared minus 10x. So half of that is 5. 5 squared is 25. But technically that's a negative 25. So then we put the 25 here. So it balances. So now we start getting that structure of 25 minus x minus 5 squared. So now I see my a squared and my u squared. So my a would be just equal to 5 because 5 squared is 25. My u is quantity x minus 5, which is fine. Its derivative is just dx. So now, obviously I got to take care of that 40. So I guess 40 du's equals 40 dx. Not that big of a deal. So we have 40, and then over the square root of 5 squared. So that's your a squared minus u squared. And then don't forget to change your bounds. So u is x minus 5. So 5 minus 5 becomes 0, and then 7 minus 5 becomes 2. And again, just like the last one I think we had for arcsine, or two problems ago, arcsine is not 1 over a. Arctangent is, not arcsine. So it's just going to be our 40, and then arcsine of u over a, so u over 5 when evaluated from 0 to 2. So then this is 40 sine of 2/5 minus 40 arcsine of 0. And remember, arcsine of 0 is 0. So really, we can just leave it as 40 arcsine of 2/5. And, it's interesting on the AP exam, I see more and more problems like this, and it's not a calculator problem, and you just leave it, right? And students feel a little bit uncomfortable that they didn't get a ratio they can do without a calculator. Who cares, right? It's some angle, great. So we found it. So don't panic if you see things like that. Okay, now next one. So I'm noticing that my if I see this is quadratic, this is linear. So maybe I should try a u substitution, like let u equal x squared plus 2x plus 1. The du is 2x dx. So, just kidding. The u is 2x plus 2 dx. So right away I'm seeing, it's not a simple u substitution. And it's close to arctangent, right? Because I could complete the square here. I can make that x plus 1 squared. But the problem is that if that's your u, your du doesn't fit. And so here's something that is sort of a little sneaky thing to do. If we're going to add 0, right? So the next two examples are sort of sneaky ways to solve this by adding 0, because this would have been perfect, right? If it was a plus 2, that would have worked out really, really nicely. So I'm going to add 2 to my problem, but then subtract 2 immediately after it. So there's my fancy 0. So my net change is 0. But let's break that up into 2 separate integrals then. So this would be 2x plus 2 when divided by x squared plus 2x plus 1 and dx, and then plus, and then the integral negative 2 over x squared plus 2x plus 1. Now, this technique may not always work, and so that's really and honestly, that's the whole point of chapter 7 is getting a whole bag of tricks, arsenal of strategies, so that when we see something, try this, doesn't work, okay, try this, doesn't work, okay, try this, and you just have to start practicing, and you start to develop these, like, oh, if it looks like this, I wonder if I can try this technique. So you start to have some of that recognition. Well, this first integral is that exact u substitution. If u is x squared plus 2x plus 1, its derivative is 2x plus 2. So that's a perfect u substitution. This would just be 1 over u du. Here, again, it's close to arctan, and if you want to think about it as arctan, you would get like a u over a. The problem is that a would have been 0, and then you can't have undefined value like that. So, so instead of that, we're going to factor that denominator, because if I factor that denominator, I can use the quantity, because it's a perfect square, x plus 1 is my u. So then let's let u equal x plus 1. The derivative is just dx. We could go ahead and multiply by our negative 2. So we have our negative 2 dx. So then that integral becomes negative 2 over u squared du. So first one, natural log, absolute value of u, plus, now this one, remember, that's really the integral of negative 2u to the negative 2. So when we bump it up a power, so it's negative 2u to the negative 1 divided by negative 1, and then plus c, which is our first time we've had a constant. Now, what was u in the first example? Again, kind of keep track, because this u is different than this u, so as long as you keep track, you're okay. So that's natural log of the absolute value of x squared plus 2x plus 1. And then the negatives cancel, so this becomes 2 divided by our u value here, which was x plus 1. And then plus c. Now, the absolute value around the natural log isn't really necessary, simply because this is always going to be positive. But if you put it, that's fine too. Okay, now this one is another one where we want to have sort of like a fancy, adding a fancy 0 to this particular problem, and so the reason being is that anything you're going to let u equal, like let's say you let u equal e to the x, its derivative is e to the x, right? And so you need to somehow introduce an e to the x, and that's really, like, people say, well, Mr. Brown, how would you know that? Well, again, knowing the nature of e, even if you let u equal e to the x plus 1, the whole thing, right? Which is great. You still need its derivative as a function in the power of e. So what I'm going to do is I'm going to add e to the x and then immediately subtract e to the x. So there's our net change, our fancy 0. And so then I'm going to group the first one. There's 1 plus e to the x when divided by 1 plus e to the x. And then here's your negative e to the x over 1 plus e to the x. Okay, so again, really, really sneaky. And then what ends up happening is this function right here becomes so we sort of sneakily added 0, and that allows this to just be 1, right? So we can integrate 1, and then negative e to the x divided by 1 plus e to the x dx. So we're going to let that denominator, like we said initially, be our u. So maybe I'll change colors here. Let's let u equal 1 plus e to the x. Its derivative is e to the x, and we're just off by a negative. So negative du is equal to negative e to the x dx. So integrating 1 is just x, right? And then this will be plus the antiderivative of, what is that, negative 1 over u, du. And that's just natural log. So we have x minus, from that negative 1, natural log of u plus c. And remember, our u in this case was e to the x plus 1, or 1 plus e to the x. Now that's also positive, so the absolute value isn't necessarily necessary. But what I can't do is separate this. I almost want to make that like natural log of e to the x is 1 and natural log of 1 is 0, which are both true statements. But unfortunately, I can't break up that sum. Okay. So then the next one and the last one is sort of on the same lines as adding a fancy 0, but it's going to be more like multiplying by a fancy 1, because I can't let this whole thing be my u, even though its derivative is negative sine. But see, the problem of letting u be 1 plus cosine is that the derivative, even though I can multiply by a negative, I can't have the derivative down there. Now I could break this up into just the integral of 1 over sine of x dx plus the integral of tangent of x dx, and we know how to do tangent, right? Because that's sine over cosine, so we've seen that one before, but we don't know yet how to integrate 1 over sine, or the antiderivative of cosecant. We will. So once we know that, then that's an alternate solution to solve for this. But I just wanted to revisit multiplying by the conjugate, or what I call the conjugate. I erase this. So I'm going to multiply by that fancy 1, if I can erase that. There it is. And that fancy 1, so that fancy 1 is going to be a difference of squares, so 1 minus cosine x over 1 minus cosine x. And so that's going to allow with the Pythagorean identity, it's going to allow the u du to line up perfectly. So a little bit of algebra, I guess. So it's 1 minus cosine squared x in the numerator. And let's just leave that factored in the denominator, sine x times 1 minus cosine x dx, because my numerator will simplify to sine squared of x, and that's sine of x. And that's 1 minus cosine of x. And the reason I liked that to be factored is because that sine will cancel with one of those. So now I can allow my denominator, sine x, to be the entire u, right? And we couldn't do that before because you can't divide by the du. So now let's let u be 1 minus cosine of x. The derivative is sine of x dx. Actually, well, it's a negative. So then that becomes positive, which is great. And so now my integral is 1 over u du, which is the natural log of the absolute value of u plus c. And in this case, I do need to, I do want to keep that absolute value. Cosine will never output anything that's bigger than 1, so this still stays positive. So I guess technically I wouldn't need that, but I would want to define my was it 1 minus cosine? I want to make sure that I don't end up taking the natural log of 0. So there are certain x's that I have to omit. Okay, so like I said, hopefully if I did this right, then you won't even notice that there was a break, that someone came to the door in the middle of the video. And if I didn't, then I apologize. So hopefully going through that kind of jogged your memory about some things we did last semester. The best way to get good at this is just to practice. And so there's no substitution for that time.